Hello, everyone. My name is from PragmaDev, and I'm going to present to you today a little bit about our company, PragmaDev, what we do, and specifically focus on a use case we had with Airbus, Defense and Space, a use case in the space domain. So PragmaDev is a software editor based in Paris, and for about 15-16 years has been dedicated to the development of modeling and testing tools for event-driven application, asynchronous system, message-based communication. The company has been actively participating in European projects or common labs, for example, with the National Nuclear Research Center, COA. So a few words on what we focus. So we develop modeling and testing tools, and for us, modeling always comes with implicit benefits, which means that we help our customers to concentrate on what rather than how, in order to ease communication between the parties, to improve the legibility of the models, to get control over productivity, to improve the quality, and of course the modeling can help to reduce development time. So in our view, for a modeling language, we think that a modeling language, in order to fulfill all these requirements, it must be complete, that is self-sufficient, be non-ambiguous, and what is more important, to be executable. What it means is that an action language should be available in the modeling language, and it also provides execution semantics. And this is what we call usually a formal language. So our tools are based on the specification and description language, which is considered the right language for communicating systems. It can help specifiers and developers to define the architecture or the structure of the system composed in blocks, which can be interconnected with each other via channels and exchange messages. Each of the blocks is a functional block, meaning that it can be furthermore decomposed into other blocks down to processes which encapsulate the functional behavior of the system. And it is this functional behavior that is expressed in finite state machines, represented in SDL, as shown in the picture, the behavior part. So basically what we have state, we have transitions which are triggered by message inputs. We can have conditions, branches, timers, and sent messages. So our tool is called the PragmaDev Studio and integrate 4 different tools, starting with the specifier, developer, the tester, and the PragmaDev tracer. So the PragmaDev specifier makes use of the SDL, specification and description language, to specify the architecture and the behavior of the system in a formal way. Being that the specification and description language is a standardized language by ITUT. The fact that the specification and description language is a formal language with executable semantics, it allows to users to actually execute and verify the model. For that we provide a built-in simulator or executor for the models. Afterwards, we go to the PragmaDev developer, which actually keeps the graphical representation of the structure or architecture of the system and the behavior in terms of finite state machines, but instead of using the SDL action language inside the behavior diagrams, it can use C or C++ code inside, meaning that it's much more targeted to developers. And there, the same interface of model execution is provided, but there we are talking more now about debugging. So there we talk about debugging real code or real application in a real target platform or operating systems. Then we go to the PragmaDev tester or the testing part. There also we propose a standardized testing language, the TTCM3, standardized also by the ITUT and ETSI. What it allows is that by describing tests in an abstract way, the users are enabled to actually test a specification, for example in SDL, or test a real application in PragmaDev developer, or furthermore a real implementation in a target platform. So from test we can test a specification or even a real application. And last is the PragmaDev tracer, which uses also a standard notation named message sequence charts. So these are basically sequence charts that can be used, for example, to trace an execution of the system, be it, for example, a real implementation or a specification using SDL. And also verify properties. So there the users can also specify desired properties for the system, which can be further verified using the PragmaDev tracer. So to put everything together, we provide support for throughout all the V-cycle, the development, starting with the specification, and from the other part we have also testing. And what we provide is tool support for actually executing the test cases with the specification together in what we call the co-simulation, and there we are talking about simulating an SDL system and testing it with TTCM3 test cases. Then going down in the direction of the real implementation, we have the design using by replacing the action language with actual code. There we talk more about real execution or real debugging. And to test this part also, TTCM3 comes into play. Going further down into the real implementation, so we have a real system now running on a certain platform, we can generate also code and executable from the test cases. So the PragmaDev specifier, developer, tester and tracer are all included into PragmaDev Studio, and PragmaDev Studio in addition to those comes with additional features and tools inside. It includes technologies which support exhaustive simulation, for example, in collaboration with Verimag. It allows symbolic resolution. We had a collaboration, a joint lab with CER. For that, it allows on-property verification and also model-based testing. So test cases in TTCM3 can be automatically generated starting from an SDL model. And of course, going throughout all the life cycle that I showed before, we can start with a specification, for example, in SDL, automatically generate the test cases from it, generate code for those, and test the real implementation of a real application. Another very important addition, which is part of PragmaDev Studio, is the deployment simulator. SDL being a very precise language, formal language with execution semantics, allows to describe the structure and the behavior of the system in terms of blocks and processes with finite state machines. However, there are cases when we want to, for example, to verify the behavior of a system of systems. Like a typical example is, for example, the IoT, the Internet of Things, when we want to deploy parts of the system in a very distributed environment composed of maybe hundreds or thousands of instances of the system or parts of the system running in a distributed environment. So to tackle that problem, we have developed a deployment simulator which allows to deploy parts of the system into a distributed environment composed of nodes. We can describe in a tabular format the inputs or the startup messages for this scenario, and then we generate a simulation model, meaning composed of hundreds or thousands of nodes and instances of the SDL blocks running on top of them. So the tool will visualize the whole topology of the nodes, will show the states in which the system is running on each node, will show all the interaction between the nodes via the messages exchanged, and then if potential problems are identified at that level, then the user can go further, investigate the problem by going inside each of the nodes and having a detailed execution trace of each of those using the PragmaDev tracer. So, last but not least, a very important addition to our toolset is the performance analyzer. As I said before, we can execute the SDL models in a very fine-grained way, so we can verify the behavior of those models. However, SDL in itself is meant for executing or verifying the functional behavior of the system, meaning that there is no time consumption concept inside the models. So what it means practically is that if I am in the execution of a certain transition, in SDL that transition doesn't consume any time or any resources. So what we did in order to address this missing part is that we defined a way to introduce timing and resource consumption concepts into the model. So what it allows is that going into a finite state machine described in SDL, we can annotate each of the symbols, meaning a very detailed description with performance attributes, with what we call performance attributes in terms of execution time and also resources and needed for execution. So we can do that at any level, meaning that we can annotate each one of the symbols in the diagram, or at more higher level, for example, one transition at a time. What is important and to note here is that we use also SDL notations for these kind of annotations, meaning the performance. So the user is able to utilize what is available in the model, like different variables, data types, and so on and so forth, for annotating the symbols with performance attributes. Then, to go a step further, what we did afterwards is that we defined a way to allocate available resources into SDL blocks. So what we mean by that is that we use deployment diagrams to describe available resources, and we attach to them the SDL blocks that we define, which have the functional behavior and the performance attributes attached to them. So this is what we call an architecture in this case. Then the next step would be to execute this model. So what we came up is that we thought of reusing existing test cases, as we were able to co-simulate a TTCM3 and SDL model altogether. So we had different scenarios defined already in TTCM3, so we reused that concept, meaning that we have a certain list of scenarios already available. We define a different set of allocation of resources, of available resources, in what we call architectures. And the tool will automatically take each of the combination or each of the pairs, will run the simulation on the background, and as a result, we'll generate a graph in which all the branches shown there will be the scenarios, and each of the lines will be the architectures. So in a nutshell, what it means that we can actually very efficiently compare each allocation. So which is the best allocation for a given scenario. So if we are near to the center of the graph, of course, that architecture is the best one compared to the others. So that's it for a brief introduction of PragmaDev and our toolset and what we do. So what I want to do right now is to give to you a presentation of a use case we had with Airbus Defense and Space in the space domain, and specifically the JUICE use case. It's a Jupiter Icy Moons Explorer. This is the first large class mission of the European Space Agency, and its objective or its goal is the detailed observation of Jupiter and its moons. So they have already defined that this mission will include a total of 11 scientific experiments, or commonly known as instruments, including ranging from cameras, spectrometers, lasers, etc. So a brief overview of the mission. As I mentioned, there will be 11 instruments that will produce data streams continuously in parallel with variable data rates. The data streams have to be stored in JUICE in a solid state mass memory, organized in files and directories. And there has been defined a file switching criteria, meaning that each of the instruments producing data streams is assigned a certain directory, and a switching criteria for the files that will be placed in that directory, meaning that when we reach that limit, we have to switch to the next file. Why is this important? Because the files have to be opened and closed, of course, created. And when everything is ready, they have to be transmitted to ground. And this transmission is done in 2 bands and in communicating sessions. So the available communicating sessions last 8 hours per day because of the visibility of satellite. And included also in this scenario is a priority management system, which means that to each data stream, or more specifically to each instrument, can be assigned dynamically a certain priority, so that certain data streams have priority to be transmitted to ground. Also, what is important here is that data corruption may occur during the transition, so there have been specified a specific protocol to handle the transmission and the data corruption, meaning that if there is a data corruption, then certain parts of the file which were corrupted have to be again transmitted to ground. So when all is complete, meaning the whole file in its integrity has been transmitted, then the file can be removed from the mass memory in the satellite. So what were the objectives of this use case? Well, the main objective, put in a single phrase, is how can we operate the satellite to maximize the amount of transmitted data with respect to scientific requests, which was not decomposed in certain more low-level, let's say, objectives, meaning to assess the data latency on board, the amount of segment retransmissions. Very important to help architects and decision makers to understand and design the system in terms of the data storage, the file size, number of files, the organization in directories, and etc., the criteria for switching the files, and the usage of the bands for downlink. Also, very important objective was that all this should be done efficiently, meaning that a simulation of 7 mission days with multiple scenarios where each scenario will take 7 mission days, of course, should take a couple of minutes and not hours of simulation times. So the architect wanted the result pretty fast. So we modeled this behavior using SDL, and basically from the description of and the specification of the model, we saw that this is a typical asynchronous event-based system. By that I mean that each instrument has to start transmitting the data, but we saw there that the files are important, so everything is organized in files. So it starts transmitting a file which is stored in the mass memory, which then, when the file is ready to be transmitted, starts the transmission via a certain band to the ground. So the model in a nutshell is composed of 3 parts. There is a controller part that will configure both the instruments and also the mass memory, and the instrument streams themselves. So it's important to mention that each instrument can have 4 streams in parallel, so in total is 44 streams of data in parallel during simulation will be generated, and the same number of directories should be available for storing files. And the communication between the parts, of course, is done via messages. So there is shown just a brief overview of one part of the model via state machine, its behavior, and also some definition of data types and the processes involved. So what is important is that the sequence of all the messages should be kept, and also very important for the result afterward is that we have precise timing during the execution, after the execution of the model, because we know exactly when the file will be created, when it will start transmitting, and when it will terminate the transmission. Next step, this is where the testing part comes into play. So having the model define the behavior of a Jewish model, then was important to configure or send different configuration or scenarios in order to execute it. So we did that via TTCN3 in co-simulation mode. So we defined the scenarios in TTCN3, and we send it to the SDL system, and everything executes all together. So as a result, we have an automated simulation of all the scenarios, of multiple scenarios. We have a fast execution and a graphical representation of results at the end. So we use the concept in the performance analysis I showed you before. And what we generate is a radar graph, which is an easy comparison between different configurations that we send and simulate the SDL model with. So in conclusion, PragmaDev Studio is based on formal languages, can help you shorten development time, reduce the cost, improve quality, ease maintenance, and what was also relevant to this presentation, optimize architecture or performance or different configuration relevant to the user. So thank you very much for your attention. And if you have also further questions, we have a poster also presenting the performance analyzer. And also, if you have any question, please come visit us at our booth. Thank you.